Hey everybody, let's talk about Git. Not the way that Git is used, but the way it works internally. Any Git beginner in the room? Well, okay, you're gonna have a hard time. We can feel your pain. Everybody else, you will find this useful, even if it's about the internals. Okay? Also, the beginners will find this useful. I want to give you a broad idea of the way it's supposed to work. So, if you want to wrap your head around Git, it's hard because it's complex. You can approach it in an onion-like fashion, right? Layers. Let's look at the layers we can remove to make Git simpler. If you look at the entire onion, you look it up on Wikipedia, it's going to tell you that Git is a distributed revision control system. That's a mouthful. Let's peel off one layer. Let's remove distribution. Imagine that there is no distribution whatsoever. There is only one computer in the world. It's this computer here. Anything is going to happen here. So now it's just a revision control system, which is still hard to get hold of because merging, branching, all that complicated stuff. Forget about that as well. Let's peel off one more layer. If you remove branching, merging, and so on, what you are left with is something that looks at your files and folders and tracks what's happening to them. A stupid content tracker. This is the way that Git calls itself. If you look at the Git man page, it's Git, the stupid content tracker. Which means it tracks history of things changing on your disk. Now let's peel off one more layer. Forget about the distinction between trees, folders and files. Imagine going to the very core of Git. And I can tell you that at its very core, Git is just a map. It's essentially a persistent hash map where you give it stuff and it returns an index. And it persists stuff to your disk. Let's start from there, okay? And then we will reintroduce the layers one by one. You have something, a piece of content, like the string something. You give it to Git. Git is giving you back a hash. That's what it is, a map. This hash is 20 bytes. It's here in hexadecimal and so on and so on. Let me do that, actually. Can everybody see? Big enough? No, let's make it bigger. Is this good? No. Okay, there is a command in Git that is made for that, and most of you probably don't know it, I didn't at least. It's a command called git hash object. It's a low-level command. It's what Git calls a plumbing command, while high-level commands that you are supposed to use in your daily work are called porcelain commands. Git has this beautiful toilet-related metaphor. Okay. So I want to do this, really, but I can't because it's not very user-friendly. Actually, it will think that something here is the name of a file. This is not what I want. I can tell it just read from standard input, and I can pass stuff to it via the echo command. Again, don't be scared by this. It's not something you will be doing on a regular basis. Maybe if you're writing scripts. But here, what I want to do is to tell Git, here is a piece of content, give me back the hash. Here it is, DEBA, not coincidentally, the same that we have here, okay? Same content, same hash. And the hash is in a format that's called SHA1, or shown for friends. So everything in Git has a shown. Every piece of content, every file, every folder, every commit in Git has a shown. That's the basic of Git, a hash map. Some people get worried about this because they say, okay, showns, so what if I have two pieces of content and I get the same shown? Wouldn't Git break horribly then? And yes, of course it would. And it's unlikely to happen. How unlikely? If you do the math, you have 20 bytes. This guy is happy. He just won the US Powerball lottery. So he won $300 million. Okay, one less problem in life. If you win the lottery, you just had one chance in 170 and so on millions of doing that, so congratulations. If you win the lottery 6 times in a row without ever losing it, that's the chances of getting a shown clash over 2 random pieces of content. So what I want to say with this, it's not going to happen, okay? Shows are unique. They're not unique in your project, they're unique in the universe. You can take every single software project on the world and put them all into the same directory, put that in Git. You get crappy performance, still no clashes. This will come useful later when we talk about distribution. For now, okay, it's a map, and I told you it's a persistent map. Where is persistence? I can ask Git to persist stuff with these other switch, -W. It stands for write, okay? Let me do that. I can do it here, and it doesn't work. It's complaining that, where am I supposed to put this stuff? I need somewhere, right? So let's create a folder with a project. And to make this a Git project, all I need is a place to persist the stuff that I pass to Git, which happens in a folder that is hidden and conventionally called .git. Does anybody know the porcelain command used to create the .git directory? Yep. There you are, we have it now. And when I open it, there is a bunch of stuff in here, in case it's too small to read. And there is in particular an objects folder that contains a couple of folders that are just for internal optimization. We will consistently ignore these ones, otherwise it's empty. Let's make it happen now. Let's hash this piece of content and persist it. Bang. And if I look in here, there is a folder here called DE, which not coincidentally are the very first 2 digits of the hash. And the follow-up of the hash is B80 and so on, and this is the name of this file. Essentially, that file is our piece of content. That's just a policy of Git to avoid the dumping everything into a single directory. It creates subfolders there. And if I look inside this file, what am I going to see? Something, not quite. It's zipped. So let me use another low-level command to unzip it and to find it, unzip it, and visualize it all at once. It's called the git cat file. Once again, you're not supposed to remember this. I can use the whole hash or just the first few digits of the hash. And if I use a -t here, it's going to tell me which type it is. It's a blob. This is Git's terminology for content. Your files are blobs. And if I say -p, this stands for pretty printing, show me what's in it, something. Okay? Good so far? Good. So it's a persistent hash map. But of course, it's not just a persistent hash map. It's actually keeping track of your files and folders. Now let me create a few files and folders just to show you that. I have here a small script to just dump a few files and folders in here. And this is the structure of my project. I have, in the root of the project, I have a README file that contains the string something. And then I have a source folder that contains 2 more files. One is file 1 that contains the string something else, and the other one, file 2, is once again the string something. Boring little project. I'm gonna add these projects to a commit in Git. For those of you who never used Git, this is more about procedures. You will learn them fast enough once you actually start using the thing. The first thing to know about Git is that with Git status, I can see the current state of my repository. Okay, there is this stupid ds store file. Blame iOS, OS X for that. I just deleted it. I have one file and one folder. First, I need to tell Git, look, I want to track this. I do that by adding them. When I say add, I'm actually essentially adding these files to a launchpad, saying this is the stuff that I want to get into the next commit. So the second one goes here, git add source, and if I do git status again, these are ready to go. Let's create a commit, which means let's create a snapshot in time of the current state of my project. Let's give it a name. This is not a good commit name, but bear with me. Now, if I say git log, show me the latest commits, I will see the commit here, okay? What just happened is that Git went out. It's a map, remember, a persistent one. It created a bunch of objects and saved them into my object database. If I look inside the object database, there you are. Now there are a bunch of folders. 5 of them, 5 folders with a file in each. Why 5? Let's see, let's explore. This is, I'm gonna go step by step. This is gonna be, require a little bit of attention. Let's start with 5D, which of course is here because it's an object in the database and it's a commit. What does a commit look like? Actually, if I look inside that file, what do you expect to see? Let's do that. Git cat file, remember this command. If I say -t, I'm going to see that it's a commit, that's its type. And with -p, here is what I get. This is a commit. Mind you, this is not metadata. This is quite literally the commit. The commit is this piece of text. Git takes this text, indexes it like any other piece of content, and dumps it into the database. It does contain some metadata. It contains, for example, the commit message, the name of the committer, the date of the commit, and something else. That's a tree. It's not actually a tree. It's a reference to a tree. It's the hash of a tree. What's a tree? I could stay here for hours.
It's a list of all the files that have been committed. A listing of the files in that commit.
Yes, it's a list of all the files in the commit, indeed. More, yes, it's a thing that contains the blobs of the files in the commit. This thing is actually, well, we know about this. It's a directory, essentially. That's what a list of files and other directories is. Tree is Git's name for, hey, this is one of your folders. It's actually the root folder of my project. It's like this folder. You don't believe me? Let's look at it. Git cat file -p. There you are. This is the tree, the root folder. And it contains a blob, the README file, and another tree, which is, hey, the src folder. It's just a snippet of text, just content, hashed, zipped, stored, easy. If you have any memory for numbers, especially hexadecimal numbers, which I don't, you might notice that this hash here is kind of familiar. It's the same hash of the something string that I hashed earlier on. Why not? That's the content of the README. Same string, same hash. This one is the hash of another tree, right? I can cat file it and what do you expect to see? Remember, there is a folder with 2 files in it. And here they are, 2 files. I will draw a pretty picture in minutes, but bear with me for a few more seconds. If I cat file this thing here, the file 1 file, the content of file 1, I see something else. And then there is the content of file 2, and once again, now even me, even with my bad memory for hexadecimal numbers, I can recognize this thing. It's the same one. Let's put them on paper because it's starting to get confusing. So what do we have here? We have a commit, and the commit is pointing to a tree. I will draw trees in yellow. That's the current root of the project. And the tree is pointing to a blob containing something and another tree. And the other tree is pointing to a file containing something else, and, well, it's reusing that one. Why not? It's the same thing. Notice that the names of the trees and the files are not in the tree and the blob. They are in the tree that contains the tree or the blob, so you can get to the same place from different directions. Git likes economy. It's parsimonious. Good. Now, bear with me in this digging exercise for another short while, because we're going to add another commit, one more. What if I edit this file and I memorize this string because I want to get exactly the same hash. So if I'm not mistaken, I expect this to be the right string, and now I can ask for the status, and Git says this file has changed. Okay, cool. Let me add it. Let me commit it with another commit message. And now we have two commits. And if I look inside the first commit, I will see the usual stuff that I expect to see inside commits with something more compared to the previous one. Can you see it? There is a parent here. This is not the first commit anymore. Now the commits are linked. This commit has a parent, which happens to be the first commit. Same hash here. Okay. Now, I won't bore you with every tiny detail here. I will just show you the final result. We have a second commit, which is connected to the first commit. And this second commit has a tree, which is the root. Do you expect this to be a new tree or the same tree that we have there? You might think it's the same, but it's not the same. The reason for that is that, look at the whole structure. This tree is pointing to a tree and a file, right? And the file is brand new because I edited this file. And this tree contains a link, in a way, a reference to the shown of that file up there. So the tree is new. The text inside the tree is new. It must be new. The other one, this one is the same. Okay, now I'm done with this structure. What I want to show you for real is the magic of it. Imagine that you want to reconstruct the state of your project at any point in time. You might imagine this involves a lot of checking and diffing and doing a lot of complicated stuff. But actually what Git can do is just to look at one commit here and forget about the link to the parent. Everything that goes down from one commit to the rest is completely irrelevant here. All we want to follow are not commit links, they are content links. And Git can follow those links and see what is reachable from there, which is essentially all that stuff up there and this file here, but not that part there. That one is reachable. Bang, this is the state of your repository on the second commit. And of course, if you do it with the first commit, same thing. Ignore everything except the content links. Everything that can be reused is reused, and you have a simple snapshot of the entire thing. It's as simple as that. One last thing about this. Look at this. We have blobs, pieces of content, files, trees, directories, stuff that contains other stuff, trees or blobs. And then we have commits. And the names of things are not in the thing, but they are in the thing that contains the thing. Does this remind you of something, anything? What does this look like?
File structure.
A file system. A file system. This is a file system. It's not a low-level file system, it's a higher-level file system built upon your low-level file system, but actually this is what it is. It's a version file system because you have commits, right? But it sure looks like a file system. No surprise here, it was designed by Linus Torvalds, a kernel guy, a file systems person. This is the best way to look at Git. It's just a stupid file system that tracks your content, okay? Not just a persistent hash map, it's a stupid content tracker. Now, give me one moment. Forget about trees and blobs. Oh, by the way, about trees and blobs, you are experts now. You know everything about the Git object model. Everybody in this room is an expert. Seriously, there is nothing else to know. There are tags, annotated tags, so you can probably study them on your own in like 5 minutes and you're done with Git's object model forever. Congratulations, by the way. I don't have the time, unfortunately, to keep following and showing you all the details of what's happening. Let's focus on the commits, okay? Let's move on to the next layer of the onion. You have 2 commits here, and let's talk about versioning features, like branches. There are branches in Git, right? Actually, if you ever used it, you probably know that there is already a branch in there. Git created it when we created the first commit. It's called master. What does it look like? If I look inside the .git folder, what do you expect to see? There must be something there, right? I can't type. So, indeed there is. I will spare you the pain of looking for it, but in here there is a folder named refs, and inside there is a folder named heads, and inside heads there is a file named master. This is your branch. Let me show it to you. Git refs heads master. There you are. What's in master? It's a shown. Remember, we have this tiny little file, and it contains a shown. Which shown is that? It's the shown of the latest commit. So essentially, what's a branch? It's a tiny little file that is a pointer to a commit. Let me draw this. There, done. That's all there is to know about branches in Git. And I'm not kidding. You can actually know this and be happy for life. There is nothing else inside a branch, ever. Let me create a new branch. For example, let me give this command, git branch fixes, that is going to create a new branch called fixes. And there, now we have 2 files in here. And the second file is going to point at exactly the same commit because, hey, we're in the same place here. You could actually literally manipulate branches by deleting or renaming and changing the content of these little files. Don't do that. So let's see what is happening here. I created a branch, bang, this is what I have. It doesn't look like a branch yet, but that's what it is. The 2 branches right now are not equal. One of the branches is special because you see, it's all green and beautiful while the other one is all white and sad because master is the current branch, which is the branch we are on right now. How does Git know which branch we are on right now. Now you can probably guess.
There's a file called head.
Beautiful. There must be a file somewhere that contains a reference to this other file that is master, right? And yes, if you did indeed guess, you guessed right, even when you guessed the name of this file. It's here right in the root. There is a little file called head. Head has this kind of mysterious vibe in Git. It's just a stupid file. And if you cat it, this is what it contains. This is, in this case, we don't have a shown, right? A branch is not an object in the database. It doesn't have its own index. So we need some kind of reference instead, and this is Git's syntax for references. So what we have is this. We have pointers, and we have a pointer to a pointer, reference to a reference. Pick your vocabulary. Now, let's see how all the complexity of branches and merges comes from this simple thing. Now I won't demo anymore. I'm sorry, I don't have the time to do that. You need to trust me, or you can follow along later on with your own computer. Imagine that I change some stuff and then I create a third commit. What happens? We know the first part of what happens. Git creates a third commit, which has a parent, the second commit. But now what happens to the branches? Which of those three files are changing? Head, master, and fixes. Which of them are changing? Is fixes changing? It's not even the current branch. Why should it? Is head changing? It was pointing at master before the commit. It's still pointing at master. Master is changing. I want to give you the pleasure of saying yes, because by now it's quite obvious. It must be changing, right? The current branch is following new commits. That is just a rule in Git. So master is moving to third and taking head along for the ride. Head is not changing, but it's just moving. Now, let me make some space here. Imagine that we do this. Git checkout fixes. Checkout in Git means give me the stuff, bring me back in time to the situation on the commit that's being pointed at by fixes. I want to move to second, in other words. What happens now? Is fixes changing? Master, head, yeah. This is what happens with the checkout. Actually, another thing happens. Git says, hey, what I see in the object repo, in my internal repo, doesn't match what I see in your current working folder. So let me just destroy everything that is in the stupid working folder and replace it with the one truth that is coming out of the object repo. Git doesn't care about your working folder, make no mistake. The working folder in your project is the least important piece of information in your entire project. So it will just wipe it out, maybe giving you a warning if you have uncommitted changes, and replace it with whatever there is in second. You have seen earlier on how it navigates trees and blobs to do that. So now imagine that we have a few changes again, and we commit stuff on the fixed branch. What happens? You know about it now. Git creates another commit, moves fixes, which takes along head, and there you are. Now they're looking more like branches, right? And now, imagine that we want to merge. What's a merge? You can probably imagine what is happening here under the hood. You have another commit, of course. It's creating another commit connected to probably new objects, for example, if you fix conflicts. And one moment. I might take more time for these. Would you mind if I keep talking for another, let's say, 8-9 minutes? We're fine? If you leave the room, I won't be offended in the slightest. Thank you. So what you want to do is to have a new commit which has two parents in this case, not just one. And why not? You can have as many parents as you wish. I think that in the Linux kernel, there is actually a commit that has like 12 parents. It's a 12 ways merge. Yeah, you can do that stuff. And you are pointing to new objects to solve conflicts. And apart from that, you just move the pointer. Okay? One last wrinkle. If I git checkout master now, you know what happens. Head is moving to master. And finally, what happens if I git merge fixes now? You might imagine that the same thing happens, right? You have a new commit that has as parents the third commit and the merge commit. But actually, think about what we are trying to achieve here. We want to achieve a situation where we have a single commit which has as parents, both in its ancestor line, not as parents, both merge and third. And we already have it. It's a merge. I mean, we don't need to create a new one. Git doesn't like this kind of expensive operations in general. It's trying to be parsimonious with the number of objects it's creating. It can get the same result by just doing this. This is called a fast forward. Every time you see a message on your screen saying fast forward, this is Git congratulating itself for sparing an object in the database and keeping your history cleaner and less tangled. I think we are done for now. There is another thing about rebases. I would hate to skip this. That's why I asked for additional time. Imagine this situation. And imagine that we want to change something in history and do a rebase, which essentially means we are on fixes. We want to change the base of that branch to be there. So we want to do this. There is a problem. We can't do this. Remember that every object in Git has an index. You change 1 byte, you get a new index, so objects are immutable, right? You can never change an existing object. All you can do is cheat. That's what Git does. It cheats if you want to do this. What it does is to copy over stuff into new objects that look exactly like the previous objects, but they must be different. Because if you follow the line of parents, that fix up there must be different from this fix here because it has a different parent. So inside the commit, you will see a different text. And that more fix up there must be different than the more fix down here for the same reason. So actually, it's creating new stuff. And then it's moving this here. And what is happening to those commits there? Yes, sir. The C++ guy said garbage collected. You said stick around for a while, and you're both right. They stick around for a while until Git decides that, hey, I can't reach them in any case, right? Unless I just jotted down they're shown somewhere, and I probably didn't. So, well, let's garbage collect them. If you want to save them for any reason, you just stick a permanent reference to them somewhere, like you create a branch. So, this is how Git graduates from stupid content tracker to revision control system. I wish I had some time to talk about distribution. I don't have much time, but just enough time to connect a couple of dots. You remember what I said in the very beginning? Shows are unique in the universe. So how do you do distribution? It looks super complicated. But actually, if you think about it, it's all about copying over the files, right? These files are unique. They have a unique hash, unique in the universe. You copy over the files, bang, you get stuff aligned on different computers. So imagine that I have, that's supposed to be local, and that's supposed to be remote, not left or right. That's an unfortunate coincidence. And imagine that I want that repo on my computer there. This is an operation that is called the git clone. How do I do a clone? Well, essentially, I copy over the stuff. I copy over the object database plus a few additional files. But it's not much more complicated than that. And after a while, time is passing by, and I might have different people working on those different repos, and I might end up with different files. This third line contains different objects in the database, different trees, blobs, commits, tags. How do I swap them? Well, there is an operation that is called git fetch that essentially means give me all the stuff there that I don't have already. Usually what you do is actually git pull, which means give me all that stuff, git fetch, plus let me do a merge because I also want to update my branches. And there is an operation called the git push that does the opposite. I wish I could go into more detail, but really it's not much more complicated than that. That's what makes it distributed, a distributed revision control system. And now we have the whole onion again, okay? Thanks. Thank you for holding on. This was longer than I expected.